Okay, so we were talking about thrust horsepower. Because back in 310, we talked a lot about the other kind of horse. We talked about brake horsepower. And then I said brake horsepower, then transforms to thrust horsepower. So now we were all the way back around talking about thrust horsepower. And there we go. Thrust is the actual amount of horsepower that an engine prop unit transforms into thrust. And that's why we lose some of the horsepower, because we can look up here where 20% is lost to friction and slippage. And it goes way higher than that if you're not in the efficient zone of the propeller. So let's see. So we'll just put this anyway. I don't know. Thrust horsepower, horsepower. I'm sorry, I didn't mean to write that word at all. I'm thinking about something else. Thrust. I remember thrust. T-H-R-U-S. Thrust is perpendicular to the rotational plane of the prop. Perpendicular to the rotational plane of the prop. I'll just throw this one up there because we did talk so much about it. Just for those of you who don't remember, brake horsepower. Even though horsepower is one word and I just made it two. It's the actual horsepower delivered to the prop. Actual horsepower delivered to the prop. Now what the prop does with it is going to be something else. To the prop. And then I want to do this. Yeah, let's go with the prop efficiency. Prop efficiency is, I'll call that PE. Prop efficiency is then equal to thrust horsepower divided by torque, or brake horsepower. I'll make this torque, T-O-R-Q, torque, or brake horsepower. All right, so one of the next thing we'll talk about is asymmetric loading. And just a good place to talk about it. Don't know why, but asymmetric loading, which means unequal loading, S-Y-M-M-E-T, asymmetric loading. So for those of you guys that have already had 300, Phil talked about P factor much? Probably quite a bit. And you had to do a bunch of orals on that, right?
Yeah.
Okay, so you remember all about it. You want to take it?
No.
Okay.
It's actually the one thing I struggled with.
Is it? All right. Where'd my slide go with P factor? Gotta be in here somewhere. I had a slide. I know I did. I even showed it to you guys the other day. What happened to it? Not that. It's not that. Oh.
Hey, Kevin.
Yeah.
How much memory do you have on that computer?
I don't know why.
Because sounds like you have a lot of stuff open, and that's gonna, take a lot of your memory.
Well, you guys having a problem?
No, what I'm saying is about when your pen starts slowing down and stuff like that.
I think I got quite a bit. I was looking for a slide that I thought I had up here, and now I don't see it, which is disconcerting to me because I sort of needed to explain what I wanted to explain. It's like, did it go away? Did I delete it accidentally? Or am I just not seeing it? Or was it in something else? Well, that's bummer. Okay. Well, we'll just go with what I got here. See if I can do it. So asymmetric loading. First of all, we'll talk about P factor. So you guys are going to talk about this with Phil if you haven't already. So P factor. Okay. So at straight and level flight, straight and level flight, both blades have the same blade angle. Both blades have the same blade angle. It was really bugging me. See if it was another PowerPoint. There's a picture. I pulled up a picture for you guys of something. And why did I pull up a picture of something? Please stand by. Enjoy, somebody play some music while I'm hunting around for what I want. There it is. It was, I wasn't losing my mind. It was next week's, but it's a perfect one to use now. Slideshow from current slide. Okay, so we're gonna focus in on this up here. And this is the prop flange, or actually this slide right here works for everything. And I use this slide to explain why you have to use this protractor and zero it out. But this is the P factor slide, really. So if you think about an aircraft in straight and level flight, then right here, then you actually have equal bites of wind, or air, I should say, on the blade coming down at us and the blade coming up on the other side, or whichever it's going to go. So it's equal. But if once the angle of attack, once the airplane starts to go up, that changes. Now this is more of a dramatic representation of it. And you can see, so this is an airplane and we just took a snapshot of it in time where it's in flight. So we can look at the angle of it hitting the air. This is this angle and this is this angle, right? So you can see that it's completely and totally different. This blade right here is taking a much, much bigger bite than this one. This one has a little bite, this one has a big bite because the airplane just started going up. So it just changed all of this. Now I bring it back down, of course, they have equal bites, but in this position, it doesn't. It doesn't have an equal bite. And if we remember which way first time I noticed that, the way the propeller rotates, all propellers are going to, especially for our here in America, they're going to rotate towards the right. So towards the right, this blade coming down has a bigger angle of attack and thus a bigger bite of air. And the one going up has a much smaller bite. In fact, it's even less than it was a few seconds ago. So what that means is, if we take a snapshot in time there, this is most pronounced when the blade is horizontal, not straight up and down. If you go straight up and down, you're kind of getting back into the same thing. So it's when it's in the horizontal position, this is when it's pronounced. So in the horizontal position, the right blade has more of a bite than the left blade. And that means the right side of the propeller has more of a grab to it than the left, which means you're actually going to start pulling the right side of the aircraft over towards the left, and you will make a left-hand turn because the right side is taking more of a bite. So that is called P factor, and that makes the airplane go to the left. And so that's different than gyroscopic precession on a prop, which is if you have a tail-wheeled airplane, when you lift the tail wheel up, the airplane wants to go left because the gyroscopic movement, which is something different. This is P factor. I'm not sure what the P stands for. I think at one point I knew it made sense, but it doesn't stand for pucker. I know that much. I think it's propeller factor actually. And so anyway, that's P factor. So it's an asymmetrical loading on the propeller. So Mark, did that make more sense than before?
Yeah, as soon as you started saying it, it all came back.
All right, so you knew it. Okay, straight level flight, both blades have the same blade angle. same blade angle / angle of attack. So they're both the same. So in C, so that'd be in a climb, the downward blade that'd be the right side. The right side has a higher angle of attack. Has a higher angle of attack than the downward blade, than the upward blade, upward left blade.
That's why you apply rudder, right?
That's why you apply rudder. So sometimes when I'm doing an oral on this one, I will ask the student, so how do you correct for P factor? And the answer, of course, is rudder, but I get these crazy things like, well, offset the rudder permanently or use a trim tab okay, so the answer to that is, so you want to do a permanent fix to a temporary problem. So P factor is a temporary problem. You're only going to have this problem when you're climbing. Once you're done climbing, the P factor goes away. So you go to climb, put in a little bit of right rudder, bring it back towards the right. That's all you do. So this creates.
What about when you're diving? Is it some factor?
Well, most people don't do a power on dive because
Okay.
So that'd be no. Pull to the left. I say to the left. I'll just leave it at that. That's good enough. All right, prop clearances.
P factor is one of the things that falls into left turning tendencies, right?
Yep, it does for me at least. All right, prop clearances, and this comes under FAR 23.925. And you know, my memory is they've actually changed FAR 23 quite a bit. And instead of having such hard and fast rules, they've opened it up. I want to say it's like ISO rules and ASE. They've gone a lot to ASE. That's the word I was looking for. Or SAE, Society of Automotive Engineers, actually, SAE standards. And it's a whole lecture on that, where the FAA has now allowed manufacturers to produce planes, and then during the production process for the manufacturer to say to the FAA, hey, look, this works under, and this is why we've done this. And if you go back to the old 23 standards, it was just the FAA saying, you will do this. You will have this much clearance between the prop and this, and you will create a plane that has this on it. And so if you look up the new FAR 23 regs, a lot of this stuff is not even there anymore, which is kind of funny. And so it's like, well, then why do I bring it up? And I bring it up because it's still on the FAA tests, which makes it a little hard because you're sort of held responsible for rules and laws that don't even exist in the FARs anymore, but yet they're still asking these questions. Thankfully, the answers to the questions, although they're not going to be located in the FARs anymore, are going to be in your textbooks. So somebody who's really quick at stuff should look up FAR 23.925. Since I'm doing it, I'm not even sure if it's still in there anymore. And the thing is, you have to make sure you're actually looking it up on FAA.gov, or you're going to end up looking it up. Yeah, I think it's still there. FAA.gov might still have this one.
Must have a clearance of at least 7 inches.
Well, that's the old one. So revisions, everything is standards. Let me see. Ooh, I think that one is amended. So I don't know if somebody has the time to go on the actual FARs on the FAA website. Don't look it up on anything else. But anyway, so this is the clearance, the prop between other things, and they're still going to ask you these questions. It's still on the tests, and so let me bring that back up. Here we go. So these are the clearances. So prop clearance is necessary to prevent prop damage from being too close to the fuselage, or prevent the fuselage from being damaged, from the prop being damaged in case you have a blown tire, something like that. So, and I'll write this stuff down for you here. Tricycle gear. So this is not a tricycle gear. This is a tricycle gear here, number 7, or 7 inches over here. So minimum 7 inches between the tip and the ground. A taxi takeoff position with gear statically deflected, and that's a quoted word right there. Static deflection simply means the amount that the spring compresses under the weight of the equipment. So, so that's under normal circumstances with a normal load, you have to have 7 inches of clearance. However, if a tire should blow or a strut should become deflated, then you only have to have a positive clearance. Tailwheel aircraft, let me see here. Minimum of 9 inches, but it's not just 9 inches, it's at the takeoff or taxi position, because obviously when this tail wheel, it's like that, when the tail wheel comes back down, this is going to go up. So it's at the taxi takeoff position. Let me go over here and look at you guys. Anybody in the class have a rating for the tail wheel aircraft? That'd be you, Harry.
Yep, I've got one.
Okay, anybody else? All right. All right, so I mentioned before, I actually took my check ride in a tail-wheeled airplane and learned in a tail wheel. So normally most people do their check ride the opposite. They learn in a tricycle gear airplane. By the way, this is also called a conventional gear. So tail wheel is also called conventional, because that was the first one. So normally you get your check ride in a tricycle, and then you have to get a endorsement and a sign off after so many hours to fly tail-wheeled airplanes. Tail-wheeled airplanes are, if you learn in them, it's just what you know, but they're a little bit of a tricky thing. If you actually were to put your feet on the rudder pedals of somebody who's flying a tail-wheeled airplane on takeoff, you'd almost swear that they're pedaling it. It's like, are you pedaling this damn thing up in the air? Because you are just going right, left, right, left, right, left, and you're dancing on these rudder pedals to keep the airplane straight. Because what happens is when the airplane is actually down on its tail, and as you lift up the tail, you have gyroscopic precession in that big old propeller, which makes this airplane want to go hard left. So you got to go quick right on the rudder, and then it starts to go right, and you got to go back left, right, left, right, left. Anyway, so I guess I'm telling you all that because one of the problems I have as a guy who, made a living doing prop strikes is to land an aircraft in what they call a wheel position. So if you look at number A right here, and this was landing, that's doing a wheelie landing is what they call it. If you do a 3-point, you actually land it with the tail wheel kind of hitting at the same time. And I learned in the Cessna 140, which was a terrible wheel landing plane. But what you have to do is you come in, and as the wheels touch, you have to go hard forward on the stick to keep those wheels planted. And to me, it just always felt like the airplane was going to nose over and smack the prop, and I was going to do a prop strike. So I was terrible at wheel landings because I was terrified of ruining the prop. So now you know my weakness. Okay, so 9 inches. We see seaplane, you got to have 18-inch between the tips and the water. Water does significant damage to propellers. You would not believe how bad a prop looks that's been hit with some water. Structural clearances down here. So structural clearance, 1 inch radially, so that's gonna be this one, between the tips of the airplane and the structure. That does not seem like very much room to me. I am a little surprised that they got away with 1 inch. It seems like it beat the snot out of the skin. But if you look at like a 310 or anything, a plane that's a twin like that, where the props are that close to the fuselage, you will see that the fuselage is really thick in that area. I think number 1, it's from vibration, and 2, in case the paint slides off and hits it. Let's see.
I have a question about the tail dragger planes again.
Yep.
So is the rear wheel stationary, or is it like a shopping cart wheel?
It's like a shopping cart wheel that is attached to the rudder, but it's not hard attached. You have springs that attach to the tail wheel that attach to the rudder. So I think the next slide, let me see. Next slide, I might have something on there. Yeah, so see, like this one, it's wrapped, it's backwards. So it will unlock and swivel all the way back around. And so normally it's just spring loaded to the rudder, And so it's got some give and take. And then if you get it too far, it breaks away from that and you have no control over it. Some aircraft have locking tail wheels where you actually have to remember to lock it. If you don't, when you hit touchdown, it's kind of like a shopping cart and it'll go crazy back there and kind of go all over the place. So there's different kinds, but most of them are like the first type I described. Oops, going the wrong way. Okay, let's see. 1/2 inch between the blades, cuffs, stationary parts longitudinally. So 1/2 an inch between the blade and that.
That seems super close.
That seemed a little sketch to me. And then the other last note is positive clearance between any other rotating parts of the prop, spinner, and stationary parts of the airplane. So in other words, that would be just positive clearance between stuff that's right up in here. So because this spinner actually goes inside of there and it's really, really close. So, all right, prop clearances, let's see. Prop clearances. So we'll preface this with prop clearance, prop clearance is necessary, well, to prevent prop damage, and reduce aerodynamic interferences, interference. Although it's hard to believe that you can not have a aerodynamic interference with a 1/2 inch clearance. Most of the time, this is not something that's really going to affect you because you're not designing airplanes, but every now and then you get into a situation where you're doing a repair or adding something and you have to make sure that you have that clearance. So tricycle gear, or as us tailwheel pilots call it, a nose dragger. So we needed a minimum of 7 inches between tip and ground. Between tip and ground. And that would be at taxi takeoff, taxi/takeoff, takeoff position with gear statically deflected.
And no tow bar near.
And then the tow bar not attached. I think that was one of my 309 slides, wasn't it? Did you get caught up with that? I'll go back to say 309. Let me see here. Oh, yep, there it is. Yes, this is the tow bar. And the tow bar is supposed to be removed before you fly away. This person's actually very lucky they don't have wheel pants, because if you have, what happened without wheel pants, the tow bar was facing forward and they took off and it swung down. And so when they land, it's going to make some sparks and bounce up and make some noise on the belly. But if you have wheel pants, it doesn't swing around. It rests on the wheel pants with the bar facing forward, and it sort of gets in the way of the propeller as you start it up. But that's okay, because I know a mechanic who can do a prop strike inspection for you with no problem at all. So, oops.
Is it you?
Yep. Oh, no, not anymore. So, let's see. Well, I'll make these notes here. So static deflection. Static deflection is simply the amount of oh, I don't want to, I said spring compresses under the weight of the equipment. Deflection is simply the amount of I'll say strut. strut deflection under normal weight.
So if your nose gear had a leak or something and it deflated, I guess that 7 inches would compensate or kind of take into that consideration so you wouldn't strike your prop.
Yep. So and then you would take it one step further. You would go, I would say worst case scenario, you would have a deflated strut and a blown tire. You should have positive clearance, which would be very, very minimal, I would imagine.
Wow. Yeah. I mean, that's a double whammy there. Both of those. That'd really bring that prop close.
Yeah. So I'll write that one. So
Have you ever measured yours, Kevin?
Nope. Only positive clearance. Positive clearance is required with strut deflated and critical tire blown. Critical tire means the one that is worst case scenario, because under some circumstances, if you blow a tire, it may actually lift the prop up a little bit. Well, then that's not the critical tire. Critical tire is the one that causes the problems when it's blown. Like you're talking about a Cessna with the prop up front, it would be the front tire. All right, so let's see, tail wheel. Aircraft, which is actually a conventional landing gear, has a minimum of 9 inches. Minimum of 9 inches, and that is at taxi, takeoff. With gear deflected. Seaplane, we need 18 inches between tips and the water. And then basic structural clearances.
Kevin, you ever flown a seaplane?
Never have. But you know, Phil, of course, has his instructor seaplane rating. That guy has everything. Between tips and airplane structure. We've got 0.5 inch longitudinally. Half an inch longitudinally between blades. Cuffs. A cuff, hopefully I have a picture at some point. Some blades actually have, well, for lack of a better word, they have cuffs. I'm trying to think of, it's like a sleeve. Well, that's almost the same thing as a cuff, right? Over the butt end of the blade. I think I have a picture somewhere. So you'd have the spinner and then you have the blade in there and then something over top of the blade. So it's this piece over the blade is what they're talking about. Where was I? Cuffs and stationary parts of the airplane. Blades, cuffs, blades or cuffs, and stationary parts of the plane. And then last point, and just positive clearance. Between other rotating parts. Parts of the prop or spinner. Prop or spinner. Prop or spinner. And stationary parts of the plane. Such as the cowling or something like that. Steven, you have a question?
Yeah, yes, I do. On if you have like multiple engines, is there a defined distance between them? Like if you have like a 4-engine aircraft, is there a distance defined?
Nah, not that I'm aware of. I'm sure there's something, but not that I know of. I could look at this and tell you they better be at least an inch apart. The props. All right, we're good, Eric. Fingers are sore. Let's give everybody. I hear a no.
No, I'm good. I'm good.
Very good. Okay. All right. Give your fingers a break here for a minute. Let's see. We'll go to right PowerPoint since I got so many of them open here. Well, that's weird. That slide went blank. Oh, well, no matter. We're going this way anyway. Okay, so let's talk about the different types of propeller configurations and how we would say it in the field. This particular aircraft, as it says on the bottom, is an air tractor. And I picked this one because this is what is called a tractor configuration. So the normal propeller where the propeller goes out front and pulls it along, that's called a tractor configuration. So you can remember that by as the air tractor. And then I will ask you, what does this airplane look like to you?
Wiener Schnitzelmobile.
Okay, Wiener Schnitzel. I haven't heard that one yet.
It's a CB.
I know what it is.
That you tow.
What kind of car does it look like?
The car from Despicable Me.
That's the best one yet. Yeah, it kind of does. It always reminds me of a VW bus.
Oh,
It
that,
looks like if someone took an Airstream and
Yeah, an Airstream.
Yeah. Yeah, this is called a CB. And it wasn't until last year that somebody pointed out the N numbers on it, which aren't N numbers at all. They're S numbers.
sexy.
Sexy, but it is spelled S-E-A because it goes in the C, sexy. I don't know. Kind of ingenious. But anyway, all right. So this would be a pusher. This would be a pusher. Now, any engine can be used as a pusher, but you guys have built the Lycoming and you know what the thrust bearing is. If you make it a pusher, it's the slinger ring on the crankshaft. And so then you have to think about, ooh, maybe that wasn't the best idea there. So, but it's what it is. The slinger ring becomes the thrust face. So, but this is the pusher type. So we've got tractor, we've got pusher, and then we've got tractor pusher, push me, pull you. And I can't think of any other types. So this one has, it's hard to tell, but it's got the prop up here and the prop back here. And anybody know what kind of plane this is?
an OV-10.
Ooh, OV-10. Is it OV-10? No.
It's
don't
a
think
black
OV10.
one.
I don't think OV10 is the right answer. I think OV10 is the Bronco. Yeah, OV10 is a Bronco. The civilian version of this was called the Cessna Skymaster 337, Cessna 337 Skymaster. The military version was an O2. So we have two of these, the civilian version Skymasters. They actually made a 336 version, which was fixed gear. And the way I read the story was that the military wanted a retractable gear, and so they made this one. This one's kind of a weird plane. I've always kind of liked them, but then I've always kind of hated them. Working on the back engine as a mechanic really sucks. It's really stuck in there. And from a standpoint of running them, it's difficult because you can't see the engine. You can only rely on your hearing. And they actually have an airworthiness directive on these engines because as the, I think it's Phil told me this one. So when they first test flew the airplane, they took it up and you have to do engine out with it. And this has inline thrust, which is a good thing, a nice safe thing. So they shut off like the rear engine and the thing picked up like 5 miles an hour. So it's like, well, that's not bad design. So it went faster without, I don't know how true that is. But I do know that when it's fully loaded, this thing only has IO 360s in it to begin with. So that's pretty small engines, and it takes both of them. As where the Cessna 310, which to me is pretty much about the same size, has 0470s in it. So it's got a lot more horsepower. So this thing has 360s. So what would happen, people would take off. And remember, you can't see the rear engine. And once you're taken off, you really can't hear it because you can hear the front engine. You just know you have this engine noise. And they weren't looking at their gauges, and you can't feel it because it's inline thrust. If you had a twin on the wings, you would feel one engine pulling you one way or the other if it wasn't working. So this one, you can't feel it. So pilots were taking off, and it didn't climb worth a dang on one engine. It almost didn't climb. Some people say, you know, you lose an engine on it, it would just, the front one takes you all the way to the crash site. So there became an airworthiness directive that you actually had to lead off with your rear engine. You had to say, you know, everybody wants to be cool and take both throttles at the same time and mash them forward. Well, this plane, you have to actually bring the rear throttle up first and get a positive indication of roll before you can bring the front engine on. So also, if you get your twin engine rating in this one, you're limited to what's called inline thrust. You're not certified to fly a twin with them out on the wings. So there we go. We got you 3 types of.
What is the point of that aircraft?
It was safe because of the inline thrust. You didn't have a critical engine out. So I guess that was the point. I don't know. Other than that, I don't know. I like the idea of them.
They're not very eye appealing.
They're not, but again, somebody gave me one, I'd be pretty happy about it. I tell you what, I kind of like them. They even make a pressurized version of these things. Type of prop configurations. I'm not a huge fan of Cessna retractables. They get stupid expensive really quick. All right, type of prop configurations. We have the tractor type. The tractor type. And that is prop mounted on the front of the engine with prop pulling. So prop mounted on the front. Pulling aircraft. We have the pusher type. A lot of seaplanes that are specifically built seaplanes, like the CB there, the reason why they did that is because you can get the prop up a lot higher because you have to have that 18 inches of clearance. Mounted on the rear. Mounted on the rear. There's some negatives to this. More susceptible to damage from rocks kicked up by landing gear, from rocks picked up from landing gear. Or water spray. And so because of that, they are usually mounted higher. You take the Skymaster, the last one I showed you with the engine in the back. If you guys haven't noticed, so like the center line of the spinner, barely above my belt, but the one in the back is almost at my head level. So it's about another 2 feet higher, 1.5 feet, 2 feet higher.
When you say spinner, what are you referring to? I don't know if I missed that.
Oh, that's probably a really good question. Let me see if I can find a picture of a nice spinner on here. There we go. That's not a nice picture. Yeah, there you go. Spinner, that's what I'm talking about. That one from slide. Let's do it. There we go. This is a cutaway, but this is the spinner right here, this big hat.
Oh, the nose cone?
Yeah, nose cone. We don't call it. It's technically called a spinner. And this one has 2 spinner bulkheads. So here's bulkhead, the rear bulkhead, and here's the front bulkhead. And these bulkheads and spinner, this spinner combination bulkhead probably costs more than a car. So I wouldn't be shocked if somebody said that spinner bulkhead combination is roughly in the $15,000 to $20,000 range. So this right here is another spinner. They're made out of spun aluminum, so they're very expensive. By the way, this one right here, this prop isn't. So you can see this prop. You can't see this prop that you can't see. You can't see that one because it's spinning. You can see this one because it's not spinning and it's in the feather position. Which is why
is that from your simulator?
No, that's actually an Ameriflight plane. I think it's
a great example of a feathered prop.
Yeah, so that's your feathered prop. Okay, so usually mounted higher, and then we have the C, the push pull, both push pulls. So push pull, push pull. Which is funny. Some people call them like a push me, pull you. And I didn't realize that was a joke until like almost a week ago. It's like, how old were you when you realized that was a joke? I was this many days old. That's from the original Dr. Dolittle movie. They had a llama that had a head on both sides and it was a push me, pull you. And my wife told me that. It's like, I was talking about something, the push me, pull you. And she's like, yeah, that's a llama. I'm like, what the hell are you talking about?
So it's not a technical term.
Push me, pull you. I don't believe it is. So I just say push pull. All right, types of props. So now we're going to cover a lot of the props that we're going to talk about. So I'll give you an overview of them. And then we're going to come back and talk in depth about them. Types of props. Now I got to go back up here so we can talk about type props. All right, so. Well, so far, this is all one we've been talking about. So we have the fixed pitch prop, and the fixed pitch prop, and I'll talk more about it, going to come in both metal, composite, or wood. And spoiler alert, composite props are really mostly just wood props with a covering over it, but they call them composite props. And you think, ooh, it's composite. What is it like? You know, must be made out of some really cool carbon fiber. It's like, no, it's wood. Okay. Then we're going to talk about the ground adjustable prop. This one actually is something that you can adjust on the ground. You would not want to adjust it in flight. It does not, but ground adjustable props. We have 2-speed props. That was the original constant speed. It only has 2 positions. It has a high pitch and a low pitch, and that is all it has. We also have what is called controllable pitch propellers. Not constant speed, but controllable. So that I'm using the actual correct terminology. So fixed pitch, ground adjustable, 2-speed, adjustable. And this particular one, it has a little electric motor up here, and we'll talk about later. And it turns this little pinion, which would turn this gear, which would rotate the blades. And so the pilot could select a higher pitch or a lower pitch out of the blade, which is, again, it's actually a blade angle, but higher higher and lower blade angles as the pilot suited, but it was not constant speed. Then there's a sore subject for me because we actually had one of these really cool and rare props, but somebody decided they wanted it more than I wanted it, and they took it. And I don't think it was a student. But this was an automatic propeller, 100% not pilot controlled, and it sensed air loads and air load. So you had you used centrifugal twisting moment and aerodynamic loads and RPM to find the right pitch for what you wanted to do. And to try and explain this, it hurts. I mean, just to understand what it was doing and how it works. But I'll kind of show you something a little bit without making you have to memorize it. I'll say, well, this kind of works like this. All right, then we get into the more modern ones, which I showed you a minute ago, which is the constant speed, which actually adjusts its pitch all by itself based upon the RPM that the pilot selects, which uses a prop governor, which is a thing up at the top, which we'll be talking about in a few weeks or so. So once you get into the constant speed props, then you get into the variations of the constant speed prop. You have just the basic constant speed prop, and then you can get into feathering propellers, which you're always going to want to have on a twin engine aircraft, because if you lose an engine, you've got to feather it. Otherwise, you have a significant amount of drag. Then we have a thing called test clubs. And so this is a test club. We have a few test clubs hidden around our shop, our lab. And what the test club is it is designed not to be a thrust prop per se, but they're a lot shorter, and it's designed to get all of the air movement very close to the core of the engine. So when you're testing an aircraft engine, you want all that wind going on, so it keeps the engine cool while you're doing test runs. And they're also designed to absorb 100% of the horsepower of the engine. Well, that is what that is. And I think it is 520, is it not? Because my clock isn't up right now.
What kind of engine is that?
I don't know exactly. I was looking for a test club and I saw that. I'm like, hey, that's a cool picture of a test club. So I kept it. That looks like a water-cooled engine to me. And I don't know, is it some sort of W? Like, is there a bank here, and one more over here? Or is it a V that's just on its side?
It looks like a W12 at least.
It's 4, 1, 2, 4, 5, and W12. Okay. Possibly. All right, 520.